Let us start today's session. In previous session, we have started with the discussion of behavioral modeling, and we have also seen what is meant by behavioral modeling and what is the difference between the behavioral modeling and the gate level modeling that we have seen in our previous session. And we have also seen regarding the structured procedures. Like in the structured procedures, we have initial block, always block. Okay, and we have also seen the behavior of this particular initial block and always block, how these blocks are working. That also we have seen in our previous session. And we have also seen that Verilog is a concurrent language, unlike a C language, which is a sequential language. It is a concurrent language. So we have also seen the concurrent behavior, right? We have also seen the concurrent behavior of this Verilog, like how multiple always blocks work parallelly, or different always block and initial block work parallelly. This also we have encountered in our previous session. And the activity flow also we have seen, like if we have declared any always block or initial block, it will start at time t is equal to 0 time unit, and every block is independent of each other. Okay, this and all we have seen in our previous session. Okay, so up to here, is it any are there any doubts or any queries regarding this? Everything is clear, right?
Sir, what is the meaning of independent thread?
Yes. So basically, in our previous session, we have seen this, right? So if there is one always block and there is an initial block declared like this, so this is one thread and this is another thread. So there is no dependency upon this initial block and this always block. These two are independent to each other. That is the meaning of this. Okay, so there is no dependency upon this initial block and there is no dependency upon this always block. So these two blocks will run parallelly. There is no dependency between this always block and initial block. And coming to this non-nesting point, so the always and initial blocks cannot be nested within each other. So this is a very important point. So we cannot write a always block followed by inside this initial block. This is not at all correct syntax. Okay, this is called as nesting. Okay, so we cannot nest this. We cannot write an initial block inside an always block, or we cannot write initial and a always block inside a initial block. This also we cannot write. This is not correct. Okay, this is not allowed in Verilog. Is it clear? So do remember, if you try to nest these two blocks, you will get an error. Okay, so these are two separate blocks, or you can say threads, which are working independent to each other. Okay, now, and behavioral statements. So this, in the case of behavioral modeling, we have some behavioral statements like if loop, case, we have loops, we have unblocking and non-blocking assignments, which have. So all this should be present inside an always block, or it should be present inside an initial block. So whether this if loop, case loop, cases and loops and blocking assignments, non-blocking assignments, everything should be present inside an always block, or it should be present inside an initial block. Okay, so inside these two blocks only, this all should be present. Outside this blocks is not at all a valid syntax. Okay, is it clear for everyone? And regarding the initial statement also, we have seen in our previous session. So the initial statement in Verilog is used to define one-time execution. That is, initial statement will start at time t is equal to 0, and it will only execute for once. Okay, and it will be executing only for once during the simulation time period. Okay, and the key features of initial block are, it will start at time t is equal to 0, and it will only execute only once during the simulation life cycle. And concurrent execution also we have seen, if we have multiple initial blocks, they all will start at time t is equal to 0, and each block executes independent and may finish at different times based on the tasks within. Okay, so like let's say if we have three initial blocks, if we have three initial blocks, this is initial block 1, and this is initial block 2, and this is initial block 3, which is present inside a same module. Okay, these three initial blocks will start at time t is equal to 0. There is no doubt in that. But coming to end of this execution of initial block depends upon the code which is written inside this initial block. Okay, this initial block can end before this initial 2 block has ended, or this initial 3 block can end first. Okay, before this initial one and initial two has ended their execution. Okay, so there is no dependency at all. Okay, everything is concurrent, but they will start at time t is equal to 0 only, but ending of this execution will depend upon the code which is written inside this initial blocks. Okay, that we will see with an example. If we give delays and what happens, what are these delays, everything we will see. Okay, is it clear? The concurrent execution is. So we have also seen statement grouping. So if we have multiple statements, we should use the begin and construct. If we have only single statement, then there is no need of this begin and end. Okay, so initial begin behavioral statements followed by end. Okay, and if there is only one statement, then we don't need begin and block. And we've also seen this, all initial blocks start execution at time t is equal to 0, and this is a very very important point. Initial blocks are non-synthesizable, and it is only intended for simulation purpose. Okay, during the test benches we will see this initial block. Okay, and during the design we don't encounter this initial block, so this is also a very very important point. So what is meant by synthesizability? This I have told you, like in Verilog there are two types of coding styles or constructs, you can say. One is synthesizable and another is non-synthesizable. So you should be very careful when you are using this non-synthesizable constructs, because these are not going to get synthesized, or you cannot use with this with your hardware. Okay, these are only for testing purpose. Okay, so you can note it down in your notes or somewhere. Whenever we encounter this particular non-synthesizable things, you can note it down. Like in our previous sessions, what are all the things you have encountered like non-synthesizable constructs? Can you remember? Basically, the code which you are writing, this is, let's say this is your code. Okay, so this code will be converted into your gate level netlist. This will be converted into your gate level netlist. This means all the physical connections will be present in this particular file, like what are the type of gates, everything. Okay, the code which you have written will be converted into a logic mapping. So logic mapping will be happening and it will be converted into a gate level netlist. This particular gate level netlist will be implemented on your hardware circuit. Okay, this particular netlist will be implemented on your hardware circuit. So basically this process is known as synthesizing. This process is known as synthesis. Okay, you can say it as synthesis. Okay, so basically in Verilog we have two types of constructs. One is synthesizable constructs and another is non-synthesizable constructs. Okay, one is synthesizable constructs and another is non-synthesizable constructs. So if you use a non-synthesizable constructs, then your particular design is not going to synthesize. That is, your code is not going to convert it into a hardware. It will not be converting into a hardware. Okay, so that is why you should be very careful when you are using this non-synthesizable constructs in your coding. So you should use them, like if you are writing your code for only testing your particular design, you can use this non-synthesizable constructs. But if you are writing your code for implementing it on some hardware, then you should only use synthesizable constructs, not the non-synthesizable constructs. And multiple blocks, so we can use multiple initial blocks in the design, not in the design. Sorry, if the design is for only testing purpose, we can use them and they execute parallel. Yeah, okay, we will continue. So we can use multiple blocks and no nesting. Nesting is not allowed in the case of Verilog. Like we cannot nest, we cannot use always block inside an initial block or initial block inside an always block. Okay, this also we have seen. And coming to an example, this is an example of a using of an initial block. So you can write a module followed by module name, and you can declare variables of reg type. And let's say if I have used wire a comma b, then whether it will be compiled, instead of reg I'm keeping wire. So whether this particular code is synthesized or whether it will be compiled first. So if we use wire instead of reg, this particular code will not be synthesized. Why? Because in our previous session also, I have told you that on the LHS side, you should only use reg data type. You should only use reg data type on the LHS side. Okay. This you should be very careful. You should only use reg data type. Okay. So that's why it is not compiled. Okay. We will get a compilation error saying that You cannot use net data type on the left hand side. Okay, so this you should be very careful. Okay, and coming to this code, within an initial beginning block, we are just assigning a is equal to 0, and hash 5 a is equal to 1, and hash 10 b is equal to 0. Okay, so basically here a few things I want to discuss now. So this equal to operator is known as blocking operator, which is known as blocking operator. Okay, and the this is known as an assignment. Okay, this is known as an assignment. A is equal to 0 or a is equal to b. This is known as an assignment. Okay, this is known as an assignment. So this assignment is happening in a procedural block. Okay, this assignment is happening in a procedural block. So why it is a procedural block? We have seen initial block and always block are our procedural blocks. So this assignment is in procedural block. So this type of assignments are known as procedural assignments. These assignments are known as procedural assignments. Since this assignment is happening inside a procedural block, so this type of assignment is known as a procedural assignment. So if you have encountered this particular term, I hope now you have got a clear idea why it is known as a procedural assignment. Okay, and the operator which we are using here is a blocking operator. We have two type of operators that we will discuss in detail in our upcoming slides. So this operator is a blocking operator. So since we are using a blocking operator in this assignment, so it is also known as blocking assignment. It is also known as blocking assignment. Is it clear? Is it clear for everyone? Now, so these assignments are known as blocking assignments, or they're also known as procedural assignments. Okay. Now, here we are assigning a is equal to 0, and we are using hash 5 a is equal to 1. Here, hash symbol followed by some number is used to give a delay, or it is used to insert a delay. Okay, it is used to insert a delay. That means this particular a is equal to 0 is happening at exactly at time t is equal to 0, and this a is equal to 1 is happening at time t is equal to 5 time units, and this b is equal to 0 is happening after 10 time units. That is total 5 plus 10, that is t is equal to 15 time units it is happening. So this is how we are going to provide our delays. Let me take one more example. So let's say if I give a is equal to 1, hash 2, b is equal to 3, and c is equal to 1. Okay. Now tell me what is the time slots where happening, the assignments are happening. Any idea? At what time a is equal to 1 is happening, and at what time b is equal to 3 is happening, and what time c is equal to 1 is happening.
At t is equal to 0, a will be assigned to 1.
Yes.
C also will be assigned to 1 at t is equal to 0.
Okay.
B equal to 3 will be assigned at t is equal to 2.
Okay. Let me tell you what is happening here. Let me brief you what is happening here. So basically, we are using blocking assignments. Okay. So the name itself indicates that it will block the assignment of particular next statement until this particular assignment is happening. So here what is happening at t is equal to 0, this particular assignment is happening. Okay, well and good. But coming to this assignment, the next assignment, and one more thing what we have discussed, it should be flowing sequentially. Okay, the statements or the assignments which are happening inside the initial block will happen sequentially, that is one by one. Okay, so what happens, the compiler will first execute this a is equal to 1. Okay, well and good. Next it will come to the second step. Since it is a sequential flow inside the initial block, okay, the compiler will come to the second assignment and it will see a delay. Okay, then what happens, if it sees the delay, it will wait for t is equal to 2 time units. So the compiler will wait for 2 time units, and after 2 time units, then what happen, after 2 time units, this b is equal to 3 assignment will be happening. This b is equal to 3 will be happening. The value of b will be equal to 3 after 2 time units. So until 2 time units, this particular execution c is equal to 1 will get blocked. Okay, so that's why it is a blocking operator or blocking assignment. That is, until the execution or until the completion of this particular execution, it will not allow the execution of further. Okay, it will not it will not allow the further executions. That is, c is equal to 1 will be waiting for the completion of b is equal to 3. So how much time it will wait? It will wait for 2 time units. After 2 time units only b is equal to 3 will be happening. Then after c is equal to 1 will be happening. So this you should be very careful. So the name itself indicates it's a blocking operator or blocking assignment. So it will block the assignment of further steps. This is one more example, module initial underscore example. This you can implement in your tool, and you can check out what are the values we are getting for a and what are the values we are getting for b, and please post it in the group. Okay, this is a small assignment, you can try it out. Okay, you can take a screenshot or something. Okay, and this is also present in the ppt also, you can check it out, the slide number. Okay, so this you can try it out in your compiler, and you can tell me what are the values of a and b and at what time unit we are getting. Okay, I think I haven't discussed dollar display statements and dollar time, right? So okay, so if you know how to use this dollar display system tasks everything, you can try it out, or else wait for me to explain those things. Okay, yeah. So that was about the initial blocks. Okay, initial blocks and the blocking statements, and a small introduction to the delays. Okay, so first we will go to the always block, and after completing always block we will come to another concepts. Okay, yeah. Now, so always block also we have seen in our previous session. So always statement is a fundamental construct in Verilog, and it enables the description of continuous or repetitive activities. Like we have seen, if we have declared simple always block, it will repeat forever. Okay, it will go on keeping on repeating until the simulation ends. Okay, like we can use it for clock generation and state updates or monitoring the signals. Everything we will see, like if we are coding that, we will see where this always block is used. And the always block starts its executing at simulation time t is equal to 0. This also we have seen, like initial block and always block will start their execution at time t is equal to 0 time unit, and it will execute continuously in a looping fashion. And it is also used to describe sequential logic, combinational logic, or repetitive logic. So we can use this always block for modeling sequential circuits as well as combinational circuits as well. Okay, we can use to model this. And always block is also triggered sensitive. That is, the execution of always blocks is also controlled by a sensitivity list. Regarding the sensitivity list also, I have discussed in the previous session. So we can also declare the sensitivity list. So if there is any change in that particular list only, the always block will be triggered. Unless and until there is any change in that particular list, the always block will not be triggered. Okay, and always block is synthesizable. Okay, so always block is a synthesizable construct. And same like initial block, in always block also, we cannot do the nesting. Like we cannot use always block followed by another always block here. Okay, this is not possible.
Hello, sir.
Yes, and this is a syntax for a always block. Okay, in our previous session also we have seen this is a syntax for a always block. At the rate sensitivity list followed by begin behavioral statements we can use, and the assignments here which are which we are declaring, the assignments which we are declaring inside this always block are also known as procedural assignments. Okay, whatever the assignments it may be, the assignments which you are declaring inside this always blocks are known as procedural assignments. And sensitivity list we have already seen in our previous session. When we are practicing the sequential circuits, this particular sensitivity list we are going to see. Can anyone tell me what is this exactly telling us? At the rate passage of clock. Like if we have always at the rate passage of clock, like in our sensitivity list we have this particular construct. Then does anyone know what is it? If we have a requirement, like this is, let's say this is our clock, this is our clock pulse. Okay, these are positive edges and this is our negative edges. Okay, these are our negative edges. Now if we have a requirement, let's say this is our design, this is our design which is connected to a clock. Okay, so if we have a requirement that our design should only check the inputs, okay, our design should only check the inputs and assign the outputs at the positive edges of the clocks only. This is our requirement. So can anyone tell me what are the examples of this particular design? Like, can you name some designs which are having the same behavior as my requirement? So I have a design requirement like my design should sample the inputs at positive edges of the clock only and produce my outputs. Okay, there it can be any logic, but my design should sample the inputs at only positive edges of the clock. So this is my requirement. So is there any design like this which is matching with my requirement? So are there any example designs like this? Basically, if we want to model a circuit which is working on the edges of a particular clock, okay, it can be a positive edge or it can be a negative edge, we can model those designs using the always block. Okay, so here we are modeling a design which is working on the positive edge of a clock. So what we are using always at the rate, this is a sensitivity list and pause edge is a keyword. Okay, pause edge means the particular always block will be triggered only at the positive edge of the clock. Okay, and there is one more thing which is known as neg edge. So basically this will work only on the negative edge of the clock. Okay, so this is what about positive edge and negative edge. Is it clear for everyone? And this design is expecting to work only on the positive edges of the clock. That is, it should sample the inputs only on the positive edges of the clock and it should produce an output at the positive edges of the clock. This is the requirement we have. Okay, so to model this particular type of design, we can use always block. We can use always block followed by the sensitivity list, that is pause edge of clock, and this design will work only on the positive edges of the clock. That is, the always block will only be triggered at the positive edges of the clock. Is it clear? Someone asks. So let's say this is our D flip flop, Q bar, clock. Okay, so this is our clock. These are my positive edges and this is my input D. Okay, okay, this is my input pulse. Okay, this is my input pulse and these are my outputs. What happens if D is equal to 0? What is my output? And if D is equal to 1, what is my output?
It follows the input actually.
Okay, yes. So what is happening is this is a positive edge D flip flop. Positive edge D flip flop. That is, sampling of inputs will be happening only at the positive edges of the clock. Okay, so let's see here. This is a first positive edge of the clock. Okay, then what happens? D is equal to 0, so output will be equal to 0. And I'm not considering any any setup time, hold time, any propagation delay. Okay, I'm considering it an ideal D flip flop. Okay, so that's why I'm getting the output at the same clock edge. Okay, same clock edge, I'm getting my output as 0. Now at the second pause edge, my design will sample the input. That is, it will check the input whether it is 1 or 0. Since it is 1, I'm getting my output as 1. Okay, now whether my design will, okay, at the third clock edge also I'm having a change from 1 to 0, so I will get a change from 1 to 0. Okay, now whether my design will detect this pulse, that it is becoming 1 at this negative edge, whether our output will become 1 at this negative edge or not. So the sampling will be happening only on the positive edges of the clock, not at the negative edges of the clock. So since there is although there is an change in the input from 0 to 1, there will be no reflection at the output at the negative edge. So only the design is going to check the input at the positive edges of the clock, and is at the fourth positive edge of the clock, our input is equal to 0. So the output will also remain as 0 only. Okay, so this is how a positive edge of a D flip flop, positive edge D flip flop works. And to model this particular circuit, we can use always block. Always at the rate passage of clock, which means it will only be triggered at the positive edge of the clock. We can write the logic. Q is equal to D in, and Q bar is equal to not of Q. Okay. This everything we will discuss, like what is meant by this operator. Okay, and this operator, what is it? Okay, don't worry about that. This is just a simple code. Always begin n. So when this always block will be triggered, and when our output will be equal to input only at the positive edges of the clock. So this is what a sensitivity list do. Is it clear? Synchronous reset and asynchronous. I think this we have discussed in our previous session also, right? It may be some design, you can say. Now tell me, this design has a asynchronous reset signal. This design has a asynchronous reset signal. Now tell me, what happens if I apply, and this design is working on the positive edge of the clock. This design is working on the positive edge of clock, and it has a asynchronous reset signal. Okay. Now tell me what happens if I apply the reset signal at the negative edge of the clock, whether it will affect my output or not. Did you all get my question? So my design is a positive edge, some design. It is working on the positive edge of the clock, and my design is using a asynchronous reset. Okay. So what happens if my reset signal is applied at the negative edge of the clock, whether it will affect the output or not? This is my question. So in our previous session also we have seen, so asynchronous reset is not going to is not going to depend upon your clock. Okay, so it may be applied anywhere. Okay, it may be applied at any time. It will definitely affect your design, and the output will be 0. Okay, now how can you model this using always block? This is my next question. Always at the rate what you are going to do, what you are writing, what you are going to write. So this is a very important point. So how to model this asynchronous reset circuits is also very important point. So we can use a always block which is working on the positive edge of a clock. So you simply write positive edge of clock. Okay, this is common, comma reset. You can write any code inside this. So this is a code syntax for a asynchronous reset. That means here you can observe this always at the rate passage of clock, comma reset. That means this always block will be triggered whenever there is a reset signal applied, or whenever there is a positive edge of the clock. Whenever there is a reset signal is applied, then the always block is triggered, and you can write your reset logic here. If reset output is equal to 0. That means whenever there is a positive edge of clock, or whenever there is a reset signal, this particular always block will be triggered, and this particular execution will be happening. Depending, actually, this particular block will be triggered if there is a positive edge of the clock, or if there is a reset signal. In the design we have seen, right, in this particular diagram we have seen, right. So at any instance of time, if we are applying a reset signal, no matter at which time, the output is getting 0. So basically this we are modeling with the help of. So this always block will be triggered at any, if we apply reset signal also. So for synchronous reset design, we should remove the reset signal from the sensitivity list. That is, the sensitivity list should not contain a reset signal if we want to design a synchronous reset signal. Okay, because this reset signal is dependent upon the posture of the clock. That is, this always block should not be triggered whenever there is a reset signal. No, it should not be happening. It should only trigger at the posture edge of the clock, And if there is a postage of the clock, this always block will be triggered, and it will be checking for the reset logic what we have written inside this, and it will be happening to 0 whenever there is a reset signal. At the postage of the clock is only it is happening, that is reset signal is synchronous to clock. With this, we have completed our session for today. So in upcoming sessions, we will see what is meant by blocking, what is meant by non-blocking, Verilog event scheduler, everything we are going to see.